we're going to look at this checklist, as I call it, or not as I call it, but as it's generally called, for graphing complicated, I wouldn't call it complicated, but graphing more challenging questions. So that's kind of the goal, right? And here comes the sometimes called algorithm for curve sketching, right? 9 sort of steps. That's what an algorithm is. An algorithm is just a series of steps. So if you do computer programming, know that. And you go through each of these steps, you can, by the end of it, have a pretty good idea of how to draw the graph, right? As each piece of information is obtained, use it to build a sketch. Determine any discontinuities or limitations in the domain, right? Are there any restrictions on the domain? Many times, if it's a rational function, there definitely is. If it's a square root function, there definitely is. If it's a square root function, then the square root has to be greater than 0, greater than or equal to 0. If it is a rational function, you look at your denominator and see what values of x will make that denominator equal to 0. Those are going to be discontinuities. That will restrict your domain. So things like that you need to look for. Determine any vertical asymptotes. Well, that's part of that discontinuity because a vertical asymptote is a type of discontinuity. Look for intercepts. Set your y to 0, set your x to 0, get your intercepts. Determine any critical numbers. That's why you set your dy dx to 0, right? Because that's where your critical numbers come from. And where dy dx is undefined. We've talked about that before. Those are where your critical numbers are. Intervals of increase and decrease. Where's the function rising? Where's the function falling? Your first derivative can certainly tell you that. Test your critical points to see whether they are local maxes or mins, right? Determine the behavior of the function for large positive and large negative values of x. This has to do with finding any horizontal asymptotes or even oblique asymptotes. As your function gets bigger and bigger and bigger, is there a value that the function is moving towards, or is it just going towards infinity or minus infinity, right? That will help you to identify horizontal asymptotes if they exist. The function values approach a horizontal asymptote from above or below. So how is it approaching that asymptote? Is it going from above? Is it going from below? d2y by dx squared gives you where you might have your points of inflection, right? And the other thing, of course, that d2y dx squared can help you to figure out, of course, is concavity, right? Determine the oblique asymptotes. Again, if it's a rational function and the denominator has a lower degree than the numerator, you probably have an oblique asymptote. Identify the function values approach the oblique asymptotes from above or below. Complete the sketch using all this information. So these are the kinds of things you want to be looking out for. And when I am putting my questions together, I'm thinking about giving you questions where it's not going to be super, super hard for you to get your derivatives. And if the derivatives are too challenging, I'll just give you the derivative, right? It's not that I'm sort of spoon feeding you, but this test is not about can you find a derivative. This test is about do you know what the derivative tells you? So if it's a case of me sort of giving you the derivative just to help the process along, I will do that. You'll see that, in fact, on the one of the homework questions. Let's give it a derivative, first and second, and say, okay, here's a derivative. What do you do with it? All right, so let's see if we can tackle question number 1. We're going to fill in this table at the end of this process. We're going to find the domain, the x-intercepts, the y-intercepts, the asymptotes, the local max, local min, POIs, that's points of inflection. Where is it concave up? Where is it concave down? Etc., etc. Then we're going to graph it, right? On the second page, or I guess the third page, or whatever page we're on, we're going to try to graph this, put this together in some kind of a graph. But let's analyze the function first, right? What parts of this can we fill in right now? Can anybody help me out with the stuff that you might be able to get from this function right now? All right, do we know the domain of this function, for instance? Let me look at the chat and see if anybody can give me some guidance on that. So you're saying infinity, minus infinity to infinity. Okay, another way of saying that, obviously, like Taj just said, is just all real numbers. So XCR, okay? X is all real numbers. There is no restriction, all integers. Thank you, Kushi. Right? There is no restriction on the domain in this case. All right, so that's something you should be thinking about as you put this together. All right, x-intercept and y-intercept. Sarah Are you saying that you know what it is because you just wrote that down? Do you know what the x-intercept is? You know what the y-intercept is. So 1/2, Sarah's thinking for the y-intercept. That's interesting. How are you getting that? I'm just curious. How are you getting that? No, actually, okay, you're changing your mind now. Um, okay, so remember how we get x and y intercepts? You plug in 0 for y. How can I get 0 from that? Well, you know what? Here's an easy one to do. What's the y-intercept? The y-intercept is 0. Can we agree on that? Plugging in 0 into this function gives us 0. So the y-intercept is 0. Now, I've said this to you before. I'm going to repeat it. If your x-intercept is 0, your y-intercept is also 0. If your y-intercept is 0, your x-intercept is also 0. What does that mean? It means that if you're going to cross the x-axis at the origin, well, it means that if you're crossing y-axis at the origin as well, because that's where they both share a value. When you're at 0, both x and y have the same value. So that's something you need to bear in mind. X-intercept and y-intercept will coincide when the x or y-intercept is 0, because they both share that particular value. Okay, asymptotes. What do you say to that? Do you see any asymptotes on this function? Anybody can come up with any asymptotes for this function? Anybody? Come on, folks, looking at the room now, and I haven't put the wheel out yet or anything. I'm just asking you all, where would I find asymptotes on this function? Horizontal, vertical, oblique, any kind of asymptote. It's not a rational function. No asymptotes. Okay, I agree. No asymptotes. It's continuous. So none. Local max and local min. All right, so I'm agreeing with you so far, right? I haven't disagreed with anybody yet. All right. Domain is all real numbers. X-intercept 0, y-intercept 0. No asymptotes. Local max and min. Where do we go for that? Right? How do we figure out where these maxes or mins might be? Come on, folks. I need some involvement and some participation here. Derivative, Adam says, and he has a question sign beside it. Need the CNs, I believe. Tar says, didn't put a question sign, but I believe means he's not so sure. And Adam is, again, with the question sign there, not so sure. Absolutely. You need the CNs. So let's combine both those answers. Adam and Taj, derivative, will give us those CNs. Let's find those CNs. Now, I didn't give you the derivative on this one because I figured that this is easy enough for you to find your own derivative. So dy dx on this one gives us, I'm sure you agree with me on this, 2x cubed minus 6x squared. I assume, sorry, can you explain again how we know that there is no asymptotes, Ariana? Thank you for the question, Ariana. Okay, first of all, let's agree that this is a polynomial, right? Ariana, this is a polynomial. This is not like a rational function. This is not a square root function. This is not a log function, not a trigonometric, none of those. It's just a polynomial. And remember when we were doing polynomials, and I know you were in my advanced functions class, one of the things that we said was that polynomials have an unrestricted range and an unrestricted domain. Okay? So I'm thinking if this is which it is, polynomial, then this is not going to have any place that the function cannot go. When you have an asymptote, it tends to suggest a no-go zone, certainly if it's a vertical asymptote, right? That function does never cross a vertical asymptote. So that would be, we can sort of, get that out of the way. The horizontal asymptotes, let's see if that would tend to suggest that you have some kind of a rational function, which this one is not. So that's why we can eliminate both of those. And then, like oblique asymptotes, none of those things would apply in this case because you need some kind of denominator for that. Okay, thanks again for that question, Ariana. All right, so 2x, let's see if you agree with me on this. You're welcome. Let's see if you can agree with me on this. It looks like 4 times a half is 2. That's x to the power of 3 minus 6x squared. So obviously we should factor this as much as we can. I'm going to factor out 2x squared out of that. So that's going to leave me with x minus 3. So you see what Kushi said back there, she said it was 0 and 3. Okay, and I would agree. If I set this equal to 0, that means that x is equal to 0 and 3. So, okay, those are my, and by the way, there is nowhere that the first derivative does not exist. There's nothing there. Don't even go there. Nothing that makes these not exist. Okay, so that's fine. That's fine. But those are critical numbers. So let's put that on the side, CNs. But this asks for local max and local min. Presumably, I'm looking for coordinates. So we need to go from critical numbers to critical points. We also need to ask, well, which one is a max and which one is a min? Because we don't know yet, anyway, right? We don't know which is a max and which one is a min. But look at what Adam did. Adam has already put in the 0 and the 3 into the original function, right? So really what we're saying is, what is y when x is 0? And the answer for that, of course, so the first one is obvious. So one of the critical points, CPs, is 0, 0. If we're going to put 3 into that function, and let me just I'm going to see if I can take Adam's word for it. Adam says it's minus 13.5 for 3. Can you all confirm that for me? We trust Adam, not to suggest we don't trust him. But, I make mistakes all the time. And I just want to make sure that we're not writing anything down that's wrong. So he says minus 13 point. I'm going to write that down. But I'm going to ask you all to check that, please. All right, minus 13.5 sounds about right to you. Okay, Sarah says yes. If I get two people on the same path, I'm going to say yes. So those are my critical points. Fine. All right, but I still don't know if it's a max or it's a min. That's not helping me at all. I still can't answer the question about whether it's a max or a min. So how do I now answer that question is what we need to figure out. Is 0, 0 a max, or is 3 minus 13.5 a max? Or are they both mins? Positive coefficient of a degree 4, Adam says, minimum and POI. That's interesting. So you're saying that just looking at the coefficient will tell us whether it's a max or a min? Is that enough? Adam, you're thinking? I think you're thinking about end behavior, right? And if you think about it, a quartic function could have a local max. Let me show you. Let me show you what I mean by that. Let's do a quick, and I'm just giving you what it might look like, right? I'll use a different color for that. I'll use maybe red. So positive coefficient could mean it looks something like this, right? That's a possible quartic function. Possible. I'm not saying this one is this function, but I'm saying it's a possible quartic function. And as you can see, if it was drawn like that, I'd have a local min, actually two local mins, and I'd have one local max. So I don't know, but there are only two extremes, sure. So you're saying what? That there are going to be two mins or two maxes, or what are you thinking at this point? What are you thinking those two? Because they're two critical points. So what are you thinking that they are then, Adam? Give me your perspective, and then we're gonna have to find a way to prove it. A degree 3. Tell me what a degree 3 0. You mean like a you mean an order 3 0 is what you're thinking? So, okay. That's interesting. That's interesting. And what about the other one? The 3, you think that's a min? That's interesting. Well, thank you. Mhm. Okay, that's an interesting theory, Adam. But how do we prove it? Thanks, Adam. Thank you very much. But how do we prove it? How do we prove what kind of critical points they are? Do we use the chart? Sarah says second derivative is positive, it's a min, etc. Yeah, there is that second derivative test as well. Remember that second derivative test that we talked about? So why don't we try that, right? Because that sometimes can be a quick, especially if it's a polynomial, right? For a polynomial, getting a second derivative is not hard at all. right? So why don't we try that? See what the second derivative tells us. So it's pretty easy for us to do that. So d2y, let me go back to black here. So d2y over dx squared would be equal to 6x squared minus 12x. Let me just double check my math here. 6x squared, okay, yeah, that seems about right. And we can plug both of these into it. So when I plug in 0, so plug in 0 into this, I'm going to end up with 6 times 0 squared minus 12 times 0 is 0. So what happens when the second derivative for one of those critical points gives us 0? What does that tell us? It fails. You're right. It actually fails. That test just, thumbs down. It just is, sorry, this is not telling us anything, right? So if it's not telling us anything, then what do we do in that case? It does fail. And by the way, let's just see what happens when we plug in the 3. Let's just do that as well. So plug in 3, and let's see if we fail on both times. Plug in 3, we're going to get 6 times 3 squared minus 12 times 3. So this is 9 sixes, 54, minus 36, whatever it is, it's positive. Okay? It's positive. Is that right? Hold on. 9 sixes, 54, 12 threes, 36. Yeah, it's positive. So, what does it mean? Why don't we use the chart? Oh, we can get to that in a minute. We'll get to that in a minute. I have no issue with the chart whatsoever. But what does this mean when we get a positive? What does it mean? Yeah, it could be concave up or down, but we're looking at the critical point now. This second derivative test had to do with testing the critical point. What does a positive critical point tell us? What is it? Is it telling us anything? Right? I put the critical point. Well, the critical number is 3. Let's say the critical number. The critical number is 3. We put that 3 into the function. It's positive. And you're saying, Ariana, that it's a max? Everybody agree with that? That when you get a positive, it's a max? What do you say to that? Everybody agree with that? It's actually a min. Yeah, it's actually the other way around, Ariana. So 3 is a min. Right? Because what's happening is that your slope is actually increasing. So it was starting off being negative, that you think of that your hand and it's doing that rotation around the curve. It started off being negative, then it sort of became 0, then it got positive. So it's increasing. So that's why you have that min there. All right. So now we know one of the points is a min. Let's put that into our chart. We can go back up to the chart and put in that point that we said was at 3 minus 13.5. All right. That's a min. Is there a max? Well, the test that we're supposed to try failed. So what we can do is use that chart. Yes, we can use that interval chart now. So let's go back up. And here are critical numbers. It's 0 and 3. Those are the numbers. So I'm going to go ahead. Little table here. How many of these things do we need now? We need to go from minus infinity up to 0, from 0 to 3, and from 3 to infinity. Now, are we going to use the first derivative or let me put some numbers in here. So let's put, let's see, minus 1. Let's put 1, and let's put 4. I like to use numbers that are pretty close to the boundaries, right? So what are we going to put inside of, where are we going to put these numbers here? Do we put them in the first derivative or the second derivative or the original function? Where are we putting these values if we're testing them out in this interval table? Does anybody remember where we're going to put them? Tomalea says it right, into the first derivative. No, not the second atom, the first. The second derivative is about concavity, and it also can be used to figure out whether you have a max or a min. But the second derivative is not about whether the second derivative, especially if it failed, right? We don't want to use that to figure out whether it's a maximum. We're going to go back to the first derivative. So let's put the minus 1 in to the first derivative, which is this thing up here. I'm back up. Let me just point it out to you. I'm back up here now. I'm going to put minus 1 into that. I'm just going to do this mentally here. And let's make sure I get this right. So minus 1 into that gives us minus 2. And then that's going to be minus 2 minus 6. That's minus 8. So I'm going to say this is negative. I'm going to say this is negative. All right, I could be wrong. You double check me on that. Let's put in 1 now. So that's going to be positive 1. So that's going to be 2 times 1. I'm doing this mentally, so bail me out if I'm getting it wrong. Minus 6 is going to be negative again. So negative again. I don't care what the actual number is. I'm just putting in the sign. That actual number is not of any interest to me at all. And then I'm going to put in that 4. So the 4 goes in as 4 3s that. So that's going to be like 64 times 2. So that's like 128. And then 16. I'm going to say that's positive. I'm going to say that's positive. So we now have further evidence that we had a minimum point, because I went from negative at the 0, 3 to the 3 infinity. I went from a negative slope to a positive slope. So that tells me definitely that this was a min, right? So that's proof positive. But over here it says I went from a negative to a negative. Uh-oh. So that's why the test failed just now. I had a negative slope. It went to 0. Then it went back negative again. What does that suggest to you? Saddle point. There you go. I have some kind of a saddle point right there. Okay. So I'm going to say there is no minimum. No, sorry, no maximum. None. Sorry about the red, folks. So that's just the way that goes. So does the second derivative test only fail when there's a saddle point? You can't just conclude that. Other things can be happening, right? So you may not have a saddle point. You may have like one of those, what you call it now, functions. So those functions that have the vertical tangent in them. So no, I don't want you to jump to that conclusion at all. For a polynomial, it generally would be a saddle point. Okay. All right. So let's see what we have here now. Let's see what we have here. We have to get a POI now. How do we get the POI? And then how do we get the concave up? And how do we get the concave down? How do we get all that other stuff? What do we look to for that? What's the tool that we need to figure out where the POI is and what sections of the curve are concave up and what sections of the curve are? It's the second derivative. That's correct. And here's our second derivative right here. So let's now set this equal to 0. And let's factor this first. And again, apologize about the red. So 6x into, let's see now, 0. What am I doing? Sorry, that's rubbish. That's rubbish. X minus 2. I'll double check that. 6x squared minus 12x, yeah. So when I set that, I just wrote in red, equal to 0, is where I have the things that I need for my table for concavity. Okay, so from this, when I set this equal to 0, I'm going to have 0 and 2. Hopefully everybody agrees with me on that. So I'm going to put another table together now. Let me go back to black, actually. I'm going to put another table together now. Using minus infinity to, sorry, was it 0 and 2? Yeah, 0. And then 0 to 2. And then 2 to infinity. I think that's what it was. Let me just double check that. Okay, so yeah, 0 and 2. Okay. So minus infinity to 0, 0 to 2, and 2 to infinity. All right, let's pick a number. Again, I'm going to go with minus 1. I'm going to go with 1. I'm going to go with 3 this time. Okay, we're just going to go ahead and plug those into this second derivative. Okay, so let me just think now. If I put it in -1, yeah, -1. If I put in -1, this part's going to be negative, and I'm putting minus, so that's going to be negative as well. So I'm going to say this is positive. All right, again, I don't really care what the actual number is. I'm just trying to make sure that, you can see, okay, just want to make sure that you see the negative or positive. I'm putting in 1 now. So if I put in 1, this is going to be positive. That's negative. So I'm going to have a negative here. And then finally, I'm putting in 3. 3, yeah. I'm putting in 3, so that's going to be positive. That's going to be positive. So this is going to be positive here. Okay, so what is that telling us? Do we have any points of inflection? Right? Does this tell us where the points of inflection are? Can anybody help me out, please? Do we know where the POIs are at this point? Remember, a POI comes from where you change concavity. Right away, we can put where the concavity is, because right now, this is telling us where the concavity is. Where is the intervals of concavity? Where is it concave up and where is it concave down? Let's answer that question first. Where's this function concave? What is it? What's the table asking us for first? Concave up. Where is this table concave up? It's not a table. Where's the graph, I should say? Where's this graph concave up? Come on, folks, help me out. I need some responses from you. Where is the graph concave up? All right, you're supposed to know what to look for that gives us a concave up part of the graph. So the minus infinity to the 0 and then the 2 to infinity. Absolutely. Absolutely. Not quite 0 to infinity. No, not between 0 and infinity. Or, no. Yeah. So from minus infinity to 0, concave up, minus infinity to 0, union with 2 to infinity. Okay. And where is it concave down? It's concave down between 0 and 2. All past Anika says, okay, hopefully back within 5 minutes, Anika. Between 0 and 2. That's where it's concave down. So we haven't answered the last question yet, which is the POI, the point of or points of inflection. Does anybody know where the points of inflection are? Does this last table here tell us where those POIs are? Where are they? Where's the first POI? 0, 0, 0. That's exactly right. Right? So the junction point between these two, which is a 0, 0, right? Where it went from a concave up to a concave down. So that 0, 0 represents one of the POIs. Oh, this is getting very crowded. Sorry about that, folks. There's another one, though. Where's the second one? At the 2. Okay, good. I see where, yes, Taj is putting in the 2. That's where your second POI is. So we need to figure out what that coordinate is at 2 for us to put in that second point of inflection. So we need to go back up to the original function again for that. And let's see if I can do this mentally now. So that would be 8 times 2 is 16 minus 2. That's 4. 6 is 24. I'm going to say minus 8. Is that right? Did I get that right? 16 minus 24 minus 8. Okay, Anika, good. Is that right? Minus 8. Am I doing that mentally right, or did I just mess that up? 6, 4 is 24. I believe that's right. Yes. Okay. So I'm going to put in 2 minus 8. All right. So that's my last answer. 2 minus 8 for my POI. 2 POIs. It's a very crowded table. Hopefully you'll do a better job than me on that. Okay, let's mark off a few things on our graph now. So let's just sort of look at this carefully now. We have, it's unrestricted domain. We have an x-intercept and a y-intercept. We know those. Asymptotes, none. Local max, none. There's a min at 3 minus 13.5. There's a POI here, a concave up section, a concave down section. So let's go over to my graph and try to put that together. I'm going to put a few numbers on here, 2, 4, 6, 8. Put that on each of the axes. Don't have to label every single one. These are negative. These are positive. Okay, hopefully I did that right. 2, 4, 6, 8. I skipped one for each one. 2, 4, 6, 8. These are negative as well. Okay, some key points that we said. One point we know is right here. Now the point that we said, let me go back and have a quick look, was at the POIs. Let's put the POIs on there. One is at 0, 0. One is at 2 minus 8. 2 minus, whoa, that's way down here. Oh, sorry, over here. I shouldn't put that in black. Okay, so that's another point that we know is on the graph. And what else do we have now? Local min at 3 minus 13.5. I'm not going to be able to put that on my graph. 3 minus 13.5 is going to be somewhere way down here. That's approximate. That's not the best way to do it. So I'm going to try to put something together. There's other thing, of course, that we know is that a function like this has end behavior going from quadrant 2 to quadrant 1. So that's kind of something we know as well. And we want the first section between 0 and 2, right? According to what this thing says, from 0 to 2 is concave down. Then the rest is going to be concave up and concave up. From 0 to 2 is where it's concave up. All right. So how about if I started somewhere maybe, remember, and by the way, the part to the left of from minus infinity to minus 2, minus infinity to minus 2 is concave up. So I'm thinking concave up would probably be something like this, concave up. All right, that's concave up. I'll put whoever agrees with me on that. And then there's probably a section which is concave down, meaning it's going to kind of turn more like this now, right? Up to this POI here, right? And then it's going to start turning the other way and then go back up. And by the way, we had the other y-intercept, x-intercept rather. Oh, hold on. We didn't have the other x-intercept. There's another x-intercept which we didn't talk about. Huh. Where's the other x-intercept? We never did talk about that. Is there another x? I'm sorry, folks. We missed a very important part of this. We said the x-intercept was 0, but we didn't see the other x-intercept. Can anybody figure out what the other x-intercept is? There's only one that we've come up with. There's another one. Can anybody see what the other one is? Can we factor something out here and get that other x-intercept? All right, look back. Let me take you back up to the graph for a second. Let me erase this. Can we factor anything out here? Yeah, you think it's 4, Richard says? Well, I'm going to factor out a half x cubed. That's what I'm going to factor out. So it's equal to, go back to black, a half black. A half, it doesn't really matter. A half x cubed as my common factor. So I'm going to let with x minus what? What's the other thing that's going to be left when I factor out that half x cubed? 4. Good. Okay, if you multiply that back out, you get the same thing. 4. Did I do that right? 4. I think I just did something. No. Yeah, 4. Yeah, there we go. Yeah. So that will give me back my half x to the power of 4 minus my 2x cubed. So my other intercept, which I totally forgot, I need to put that up here. So 0 and 4. All right, so we'll put that on as well. So up here in red. All right, not the most elegant looking graph, but let's just see if it kind of makes sense based on all the things that we know, right? we said that this was going to be concave up from minus infinity to 0. That does look concave up to me. Let me say it's going to be concave down up to 2. Let's go down to 2. So concave down up to 2, then it starts to curve the other way, and concave up then goes that way, concave up right up until infinity, right? And it does cross through the points that we said we wanted to cross through on the x-axis. It does seem that the change on concavity happens at about 2 right here, with a minimum point down here. So it all seems to fit together nicely with what we expected from the features that we came up with on the graph. Minimum, the POIs, the concave up section, the concave down section, all that stuff makes sense. Okay? The other thing you might want to look at is where's the function increasing and decreasing, and that just is a matter of graphing the derivatives. If I were to graph this thing here, which is not that hard, wherever this thing is positive, the function is rising. Wherever this thing is negative, the function is falling. Just FYI. Okay? All right, so that takes care of that question. Let's move on. Unless there are any questions on that, I'm going to move on to the next one, which, yes, is going to be a little bit more challenging. It's a rational function. So that's this one here. And if you can see, I have been nice to you, and I've given you the first derivative and the second derivative. They're both there, right? So I'm going to make this bigger for you, so you can actually see it a little bit better. So I put that there, and this is the second derivative right there. And you're welcome, by the way, right? See, I'm sort of not giving you the grunt work of having to come up with a derivative because I just gave it to you. All right? Okay, so if I then give you that and I ask you about some things, let's see if you can answer me now. Let's start off with the domain of the function. What would be the domain of this function? Now, look at this one is a rational function. So ask yourself about things like asymptotes, right? Specifically, it's because it's domain, we're talking about possible x values. So not so much horizontal asymptotes, but vertical asymptotes. Do you see any vertical asymptotes here for this function? Can anybody see any vertical asymptotes for this function? And if you see one, let me know what it is. The VAs, that would restrict the domain. The other thing that restricts domains is, like I said, square root functions. Not cube root, but square root functions, or any even root, you would have to have a positive number. But how about VAs on this one? Do you see any VAs on this function? Anybody? Come on, folks. You see the denominator? Focus on denominator. Richard says no VAs, really? Anybody want to jump on that? Anybody want to say yes? No VAs? Really? So Anika, x equals 20. Okay, so some people are thinking it's 25. X equals 25 for Jordan and Stephen. You can't take the root of minus 25. And that's the point Sarah is making. There are no VAs here, right? Okay, Alicia. There are no VAs here. I cannot make the denominator of this thing equal to 0. It can't be done. You take that x squared plus 25. I'll just show you quickly. Set that equal to 0. There is no solution. There is no value of x that's going to make this equal to 0. For this to be equal to 0, you'd have to have some minus 25 to add on to that positive 25. And this is being squared, so there is just no way to make it 0. So there are none. So it's XCR. It's all real numbers, right? It's a continuous domain. Nothing is getting in the way of this domain. It's a continuous domain. Something to bear in mind. X-intercept. Can anybody tell me what they think the x-intercept of this is? Come on, folks. You know how to get an x-intercept. Set the the y to 0 and solve it. What's the x-intercept of this function? It's 0, of course. And if the x-intercept is 0, what did we just say is the y-intercept of the function? It's also 0. So let's just dispense with that. Are there other x-intercepts? I know the last time we got the first x-intercept and then we kind of forgot that there might have been more. Are there any other x-intercepts? Is there any other value that would make that become 0? Anika doesn't think so, and you're right. So only one x-intercept, only one y-intercept. That's it. That's all. Okay. Asymptotes. Well, I think we already agreed that there is no vertical asymptote. I think we already agreed on that. Is there any other kind of asymptote though? Like maybe a horizontal asymptote or maybe an oblique asymptote. What would your answer be to that? Okay, so Nika says no horizontal ones either. Interesting. Okay, Richard says there is a horizontal. Taz says yes. And Richard says yes, the y equals 0. And you have to remember, you compare the degrees of the numerator and denominator. And in this case, the numerator is degree 1. The denominator is a degree 2. So when the top is less than the bottom, then yes, there's a horizontal asymptote. That horizontal asymptote is the x-axis or the y equals 0 line. So bear that in mind as well. Okay, so there is a horizontal asymptote. Local max. Ouch. Okay. So we've done this before. We did this on the last question. And the way we did that is, I forget. Help me out here, folks. How do we figure out if there is a local max here? What do we do, folks? Local max. Is there one, and how do we find it? The derivative. First or second? Which one do we use? Sarah and Adam said derivative. The first, absolutely. So our first derivative is what you see there. Again, I'm not asking you to find a derivative. We've already, that's in a previous unit. So hopefully you can do that yourself. So is this 25 into minus x squared plus 25 over x squared plus 25 squared? So let's just write that down because I think you know that you need to set that derivative equal to 0. So it's 25 and it's factored out as minus x squared plus 25 all over x squared plus 25 squared. Does anybody know how to solve this? Do we look at the numerator and denominator or just the denominator? Oh, equal to 0, sorry. Does anybody know how to solve this? All right, where do we look? We look at the numerator. Thank you, Adam. So we're just going to ignore the denominator because if you were to cross multiply, meaning take the bottom of this side, multiply by the top of this side, you're going to get 0. So it means that the whole top is where you want to get 0. So let's put that. So 25 minus x squared plus 25 x squared is equal to 0. Okay, I've done that. So where do I go now? How do I solve this now? All right, what's next? I need to solve for x, folks. I need to solve for x. So how do I solve for x? Any ideas? Factor out the minus 1 and then difference the squares. Actually, you know what, Adam, you're right, but I don't even really need to do that because here's, what if I wrote it this way? 25 minus x squared equals 0. Wouldn't that be the same thing? Adam is saying, yeah, it is the same thing, right? I just put the x squared second and the other one first. And of course, that means that I can factor that as a difference of squares. You're right. 5 minus x, 5 plus x. Yeah, that's absolutely right. This 25 is of no significance whatsoever because I can divide the two sides by 25 and it's gone. Okay? So what that means is that I have two values of x that will make this equal to 0. And what are those two values of x? And we factored it. What are those two values of x that will make this make this function equal to 0? Adam is right. Looks like only Adam is, no, I can't say that because other people have been contributing. Anyway, so plus and minus 5, x equals plus and minus 5. Okay. But that's not, the question is, let me go back up and show what the question is again. Local max and local min. I don't know whether that's a max or a min. I don't know. I have no idea. How did we figure out whether it's a max or... And by the way, we also need to know what the y value is for this. So let's quickly do that. And I'm going to remind you, because in the interest of time, oh, wow, this class is just fading fast on us. In the interest of time, I'm just going to say that we're going to go back to the original function for that, which is a 25 over x squared plus 25. So let's plug that in. So y equals 25x over x squared plus 25. So 25 times 5 over 5 squared plus 25, was it? Oh, geez, I don't remember again. Yeah, okay, all right. Top of this is 125. The bottom of this is 50, no, yeah, 50. So 125 over 50 divided by 50 comes down to 5 over 2. If I put minus in this instead, then the only thing that's going to change is the top, I think. So that's going to use a chart for the second derivative. Okay, Sarah, thank you very much. So let's just put the coordinates in. We don't know what is a max or a min yet, but let's just say that the critical points are 5 over 2. What is this? What did I put in before? Minus. Okay, so 5 over 2. And minus 5 over 2. Okay? So Sarah is saying for me to get whether it's a max or a min, I need to use the second derivative or the chart. Which one is going to be easier? Well, because I've given you the second derivative, I'm going to say, let's just use the second derivative. All right, let's just use, I mean, the chart is one way to do it. And again, it's the question of your own personal preference, right? What do you find easier? Well, that's your call. Okay, you got two choices. Just remember that second derivative test can fail, which means that you might have to go back to that first derivative anyway. But I'm thinking if I have that second derivative, I'm just going to go ahead and use it. So the second derivative says minus, and I'm putting in the 5 and the minus 5 into that. Let's see what, in fact, since it's right here, let me just clone this so I can have it close by here for me to do this for 5 and for minus 5. And you can tell me which one is a max and which one is a min. Okay? So here we go. I'm going to say that the y, this is for the second derivative now, is minus, here's a minus in front, 50 times 5 over minus 5 squared plus 75. And the truth is, actually, the bottom could be negative. So actually, the bottom can be negative because I'm going to square that. So the bottom is going to be positive for sure, right? Because it's x squared plus 25, which is going to be positive, raised to the power of 3. So the bottom is always, okay, Alicia, the bottom is always positive. Let's see what happens to the top. So let's just see now. This would be minus, that's going to be positive. That's positive there. That part's going to be negative. It's going to be negative. All right, please check me on that. Just make sure I'm not messing up here, because I believe that would be right. That first part's going to be negative, and if I put in negative 5 this time, so minus 50. What did I just put in? Okay, yeah. So minus 50 times minus 5, and then I'm going to put in minus 5 squared plus 75. That part's going to be positive. That part's going to, so I'm going to say this is positive. Okay, what conclusion can we draw in the time that we have left? Oh, geez, this is, I don't know where the time goes. What conclusion can we draw about the positive 5? What conclusion can we draw about the negative 5? What does the answer of negative, a negative one put in the positive 5 tell us? Come on, folks, help me out. What does it tell us when we put in that 5 and we get some max? There you go. So I'm going to put that in right here. The local max is at 5 over 2. And the local min, because it turned out, I'm just reminding you, when I put in the negative, when I put a positive, I got negative. When I put in the negative, I got positive. That means that this would be a min at minus 5. It's minus 5 over 2. But that's terrible. I need to make these boxes bigger. Yeah, clearly need to make them bigger. All right, thank you, Danny. So it's a max. It's a max when it's negative, it's a min when it's positive. All right. POIs. POIs. Concave up, concave down. I don't know that we're going to be able to finish this, so let's see how far we can go. Right? Where is it concave? And where do we look for that again? Where do we look to figure out where it's concave up and concave down? By the way, did I use the right thing for the look? Yes, I did. The minus 50. Okay. I use a second derivative and set that equal to 0. Good. Okay, so here's my second derivative. Again, it's right here. So I'm going to clone that again. If I set this equal to 0, right? Again, it looks like it's the top that really we need to focus on. Can you quickly tell me, so regarding the group sketch, how far homework is that still for tonight or for tomorrow? I think we have enough here, Danny, for you to get that done. I can't set up groups because I just don't have time for that. But I think we can. I think you can at least. I tell you what. Just do the first one for now. First one I think is a polynomial, and then I can probably get you to do the second one tomorrow night. So let's agree on that then. It can't be a group assignment because I just don't have time to set up any groups right now. But just go to today's assignment, click on the link, get the first one done. And so what I'm going to be looking for when I do a homework check on that is that the first one is done. So I probably do 2 separate homework checks, one for the first and one for the second. Okay, very quickly. Let's get to this second one. Let's get to this thing here now. So I need to set this equal to 0 to figure out my concave up, concave down sections. The top of this is, let's just write it this way. Now remember, I'm looking for where this is equal to 0, right? And so again, just focus on the top. So it's minus 50x into minus x squared plus 75. And can we agree that there are 2 values that are going to make this equal to 0? What are those 2 values? Can anybody quickly tell me what those 2 values are going to make this equal to 0? There are 2 of them. Actually, 3 of them. Sorry, there are 3 of them. There are 3 things that will make this equal to 0. One of them is 0. Let me just get that out of the way. But there are 2 others. 0 for 1. Yeah, I agree with that. 0 plus and minus 5 root 3. Well, it's the square root of 75, which is in fact 5 root 3. So it's plus and minus 5 root 3. And I don't want any decimals in this. The table specifically says, complete the table with exact values only. Exact values only. So the thing I'm going to be doing now, quickly, is I'm going to say, okay, we have what, 3 different values here. So I'm going to go from minus infinity up to minus 5 root 3. Then I'm going to go from minus 5 root 3 up to 0. Then I'm going to go from, the other thing I need to, the other thing I need to ask about is, can this denominator here be 0? Because that is, in fact, something we need to talk about. I forgot to ask that question. Can this denominator here be 0? Is there any value of x that can make this equal to 0? For that to happen, right, you need to be able to get a minus 25 from this, and then that will make this 0. But I can't think of any value that's going to make that happen. So let's just keep going here. From 0 up to 5 root 3, and then from 5 root 3 up to infinity. Okay, we need to find numbers in each one of those intervals. 5 root 3 is approximately 8.6 something. So let's say minus 9 for that. Let's say this would be, I'm just going to use a number like maybe minus 1. I love minus 1. I use 1 for that. And this one I'm going to use positive 9. All right. So that's probably about as far. Actually, you know what? I'm going to leave it there. Because I do need to speak to 2 people before we finish off. So the homework is just to do the first graph, right? The first of this sketches. And then the second one will be for tomorrow.